Next we have André Pacak, and he's going to talk about interactive debugging of Datalog programs.
Okay, thank you for the introduction. This is joint work with my supervisor, Sebastian Erdweg, and we are both from the Johannes Gutenberg University, Mainz in Germany. Datalog is a logic programming language that has been invented in the 80s, and it has some really cool properties. It has, for example, an incremental execution model, and it has a declarative least fixed point semantics. And the interest in Datalog has risen quite a lot in the recent years. Here you see the number of publications in the last 20 years, and in the last 10, the number of publications rose a lot. So a Datalog program is a loose collection of Datalog rules, where each rule has a rule body and a rule head, and a Datalog rule forms a logical implication. This program here in particular derives the path between nodes in a directed graph. And here is a visual representation of a graph. And to run a Datalog program, we need to encode this graph in a set of facts. And then we execute the Datalog program, and that means that the Datalog solver will apply these rules over and over again until a fixed point has been reached. And these derived facts then are the output of the Datalog program. Datalog was invented as a querying language back in the day, and the programs back in the day were rather small. They were in the size of SQL queries, for example. But nowadays, Datalog is actually being used as a programming language. And here we see, for example, a dependency graph between relations between relations for an intra-procedural points to analysis for Java that is provided by the Dupe framework. And all these bluely colored nodes here describe one big fixed point computation. So these programs get bigger and bigger, and naturally there will be bugs in the program. So we need some way to debug these programs. And here we have a small Datalog example that derives the typing relation of a lambda calculus term. And this program contains a bug, but you don't need to look for this right now. So what would we do to debug, for example, imperative programs? Well, we would identify a failing test case. We would then set a breakpoint. And then we would run a debugging session, right? So let's use these ideas and debug this program together, but we do this for Datalog. We identify this failing test case, and we suspect there's a problem with typing applications. So we set a breakpoint in the application rule, and then we start a debugging session. And we hit the breakpoint, and up until this point, this app call deconstructed the expression E into the function E1 and the argument E2. The next call, typeof, will type the function and expect it to be of function type. We just step over this, and up until this point, everything seemed fine. And then the next call seems a bit weird, right? So there is this, we want to type the argument expression, but we expect it to be of type NOT. So let's step into this and see what happens. At some point, we will arrive at this rule, where the rule says every Boolean expression should be of type bool, but the variable bindings indicate, well, this is a Boolean constant, false, and we expect it to be of type NOT. And what happens is that this rule is not applicable, so this variable binding will disappear. And that means this rule is not, so this rule will not derive a tuple. And all the other rules will also not derive a tuple because these are syntax-directed rules, basically. So the problem was that we typed this argument expression and were too restrictive here. We wanted to be of type NOT, but actually want to have the argument type of the applied function. So we successfully identified and fixed the bug for this buggy program. So what we need for Datalog is an interactive debugging experience that is very similar to debugging imperative programs, for example. And this includes interactions such as setting breakpoints, inspecting the call stack, inspecting variable bindings, stepping into calls, stepping over calls, and resuming the computation. And up until this point, there does not exist such a debugger yet for Datalog. So to find and fix bugs, we need to follow the top-down stepping order of Datalog. But there's a so we want to define this top-down stepping order by defining a small step operational semantics, because this operational semantics defines every step at which we can stop. But there's a problem, because there does not exist a small step operational semantics for Datalog that follows the top-down evaluation order. There are algorithms for top-down evaluated Datalog, like subquery, for example, but all these are described as pseudocode in the literature. So most of you know how to describe small step operational semantics for languages like the Lambda calculus and its extensions, or imperative programming languages, like introduced in the book Types in Programming Languages. But what is special about Datalog? Why is it hard to define a small step operations semantics for Datalog? There are a few differences. For example, the values Datalog operates on are actually not primitive values like booleans and strings, but they are actually tables, and we need relational operations to operate on these tables, for example, joins and filters. Variable bindings in Datalog are tricky. They are very implicit. So just by looking at the syntax, you cannot be sure if this is a binding position or if this is a referencing position. Datalog is non-deterministic. That you, to derive an answer for a query, you need to try to apply all rules. But most importantly, Datalog has an implicit least fixed point computation over this loose collection of rules. So somehow we need to figure out when do we need to restart the fixed point computation, and we need enough information to actually restart it. So the goal of this paper is to define a small step operational semantics for top-down evaluated Datalog, and we use that as a basis for a debugger. And this small step operational semantics should be as standard as possible. And we follow the top-down evaluation strategy, query, subquery, that is known from the literature. So let's start defining the small step operational semantics. We start by defining the abstract syntax for rules. And we define a rule reduction relation that reduces a rule under a current set of bindings, and it also updates the set of bindings after reducing the rule. And as with all small step operational semantics, there's a concurrence rule that reduces the first atom in a rule if it can be reduced by an atom reduction relation, and it just replaces it with the reduced form. When the atom has been fully reduced to a value table, then we will discard this value table and update, merge this with the current set of bindings to update the set of bindings. And in the end, if all atoms have been reduced and the values have been merged into the set of bindings, we reduce the empty rule with a projection of the current set of bindings. So that seems pretty straightforward. But what was challenging about Datalog? Well, Datalog uses fixed points, or has fixed point computation. So we need to look out for two things. First, we need to avoid that we run into an infinite loop, that we see the same query over and over again to force termination. And secondly, we need to somehow figure out when do we actually restart the computation and when we are stable. And to do that, we've split this fixed point computation into three parts. The AInter rule marks the entry point of the fixed point computation and creates a new query. QIterate then restarts this query over and over again as it discovers new tuples. And QStable then marks the exit point of the fixed point computation. Here are these three rules. They are quite complicated. I don't want you to read them, but I want to highlight how we address these two problems. To avoid running into an infinite loop, we keep an active query stack. And in AInter, we push to this query stack. And in QStable, we pop from the query stack. To figure out if we need to restart the fixed point computation again, we have this global map called IDB that stores all currently derived tuples. And qiterate is only applicable if new tuples have been derived, and then it extends the IDB accordingly. And qstable is only applicable if no new tuples have been derived in the last iteration. So up until this point, we defined a stepping into semantics for top-down evaluated data log, and it fits on a single page. The semantics can be used to prove the correctness and soundness of this query-subquery recursive algorithm, which we actually did not do in this paper, but we heavily tested it against existing bottom-up data log solvers. And I invite the PL community to use the semantics as a basis to define meta theory about data log. For example, prove type soundness or correctness of the optimizations, and also explore new data log extensions. Based on this debugger, we implemented, based on the semantics, we implemented a debugger for the data log intermediate representation that is part of the IncA framework. And because we can compile functional IncA programs and some form of Soufflé programs to this intermediate representation, we can also debug both of these types of programs. So up until this point, we only talked about step into, but what about step over? Well, we could simulate step over with repeated step into interactions, but there's a problem. Top-down evaluate data log, the performance is very poor for that strategy, and that's why all serious data log solvers actually use bottom-up evaluation, in particular semi-naive evaluation. And I want to highlight, visualize this with this graph. Here we have the path program over where we compute with top-down evaluation strategy and bottom-up evaluation strategy on cyclic graphs with a rising number of nodes. And you see that the top-down evaluation skyrockets in the running time. And the problem is not that each interaction, each step takes a lot of time, but the problem is actually that we need a lot of steps to actually compute the fixed point. So to address this problem, we want to combine top-down evaluated data log with bottom-up. And what we do is we use a bottom-up data log solver that we use to derive a bottom-up database. And we use this database to inform the top-down stepping semantics whenever we want to step over a call. And all these technical details, how we do that, are described in the paper. I'm not going into that. So we have this idea about this combining of top-down and bottom-up for step over, but does this actually work? Does it give us responsive interactions for step over? We measured that on a dupe analysis, a Java points to analysis, that also analyzes parts of the JVM. And we described a few scenarios in the paper where we then measured a lot of step over interactions, and indeed it's actually feasible. Most of the step into interactions take at most 70 milliseconds, so it's quite responsive. To conclude, to identify and fix bug in the data log program, we need to follow the top-down stepping order. To define the semantics of this debugger, we actually defined small step operation semantics. And again, I invite the PL community to use this as a basis to define meta theory and explore new data log extensions. To provide responsive step over interactions, we combine top-down evaluated data log with bottom-up derived databases. And this makes interactive debugging actually feasible, and the interactions are quite responsive. Thank you for your attention.
Hey, so interesting talk, interesting work. Does stratified negation, is that something you can support?
Yes. So we had this in the rule, which I'm too far ahead, sorry. Yeah, but basically we can support that. Why doesn't it skip? Let's see. Where is it? This rule. So this in our merge we have this value table that has this sign at the top, and there we track if this was produced by a positive or a negative call, and based on that the merge operation then uses a join or an anti-join. So yes, we can support stratified negation.
Okay, thanks.
Thanks for a good talk. So can you say a bit more about what breakpoints mean? Do you do the top-down semantics to step actually to the place where it hits the breakpoint, or can you somehow use the database from bottom-up evaluation to just jump to where that comma is actually used?
No, we actually do the first strategy you described. So we set a breakpoint and then we use as much as step over interactions as we can use to actually trigger this breakpoint. So, yeah.
Maybe just one more question. So how does this compare to debugging with provenance information, for example?
Yeah, provenance is another approach to debugging Datalog programs, where you actually use proof trees, right? And but the problem with provenance is that you actually need a ground tuple to actually inspect the proof tree, and also if you want to inspect if how a tuple could not be derived, you don't have any proof tree. And what we do here is we actually follow the computation. We can also, as for example in the debugging session I showed you, I didn't describe the type I wanted to inspect. Also this test case failed, so there was no proof tree to inspect. So we can actually follow the computation and expect what's happening.
All right, well, let's thank André one more time.